right. Greetings, YouTube. We are back. Didn't really move that long. Come in the background. There we go. All right. So this is a beautiful mind here, and let's see. So this is going to be our Cal one. This is going to be week 3, Monday. Lecture for Calculus 1. We're going to go ahead and move into derivatives. Okay. So I think last time we talked about limits. Let me pause and see if there are any announcements that we need to discuss. Oh, let me bring this closer. So I think exam one was due this past Saturday. It's on Pearson. Keep in mind that you can actually submit assignments past the due dates, but there's gonna be a penalty. So the highest you can make on any assignment is like 80%. Oh, another note. So I did go ahead and reduce the number of questions because I do feel like they would take a long time, at least for when they were posted. They were posted kind of late. So I did kind of reduce. I cut like the amount of homework questions in half. I think we had exam one due this past Saturday at 11:59. Keep in mind you can submit assignments past the due date. I think on all assignments the highest you can make is an 80, which is a low B, and on exams I usually do 79%, which the highest you can do is a high C. Okay. So again, as you kind of go through the material, take notes as if you're in class, write down your questions, and you have to email me. You have to reach out, and and so my intent with posting these lectures, I'm doing the best I can to post the lectures early before class, so that way during class I can just be available for questions. A lot of this material is my first time presenting it at GMC. I do have another person in attendance. Now, if you are one of my current students and you're not in my calculus course, you can still, if you ever see that I'm live, I'm monitoring my live chats, so you can actually go ahead and take advantage of that. So you can say, hey, this is so and so. I'm in your this what so and so class. Um, and if it feel like it doesn't take too much time, I don't mind responding. But I do try to be available during class time for questions and answers. I also do my best to be available during office hours. All right, so I can't think of anything else. So let's kind of go ahead and get into the material for today. I hope everyone had a great weekend. Hopefully, we were able to get our assignments in on time. Another note, a couple of other notes. So on Moodle, we have this participation and honesty quiz we need to go ahead and do. So on Moodle, and I think I put it in week 3. I had to check that actually. Let me go ahead and check it now since I'm here, because I'm not sure that I did that. Mm. Yeah, let me make sure it's there. Week 1, week 2. Yeah, I need to make it available. Let's see, where did I put it for you all? Okay, so yours is in week 1 for right now. Where is it? Not that one. Where is the thing? Here's week 2. There it is. So yeah, let me make week 3 available. Okay. So yeah, in week 3, there's this link that says participation in academic honesty verification. We need to go ahead and take that, and just go ahead and submit it there on Moodle. Okay. So yeah, we're gonna go ahead and move forward with today's material. Okay. So again, I did pull this directly from the text. I didn't really like the PowerPoint lecture slides. I don't know, they didn't have enough information for me, and I was kind of taking a lot of those out of context, and they didn't have examples, so I was just like, you know what, let me just pull it straight from the text. That'll be easier for me. So we want to move into derivatives. I'll do my own little intro or disclaimer first. So we've actually discussed a derivative. Derivative is nothing. So it's nothing but the slope of the tangent line. So I think earlier we had a curve, and we chose like 2 points on the curve, and we kind of saw we considered sorry yeah, we considered the slope of the secant line, and we observed how the slope of the secant line changed as that second point got closer and closer to the first point. So the derivative is going to be a function that describes, you can describe the the slope of the tangent line across the whole curve. That's essentially what it is. It's all about the slope of the tangent line. And then so we're going to be plotting x versus all of those slopes, and it produces a new function we call the derivative. Okay. So let's start with this chapter preview. So now that we're familiar with limits, so I think last time we talked about the limit, we talked about how as a second point gets closer and closer to the first point, or as like x goes off to infinity. All right, we discussed those different kinds of limits and how they could arise. So now that we're familiar with limits, the door to calculus is open. The first task is to introduce a fundamental concept called the derivative. Let's go here. So suppose a function f represents a quantity of interest, for example, the variable cost of manufacturing an item, the population of a country, or the position of an orbiting satellite. The derivative of f is another function denoted f prime that gives the slope of the curve as it changes with respect to x. All right. So it'll tell us the instantaneous slope of the curve as it changes with respect to x. Equivalently, the derivative of f gives us the instantaneous rate of change of f with respect to the independent variable. We use limits not only to define the derivative, but to also develop efficient rules for finding derivatives. So that's going to get into section 3.3. That, to me, that section is a lot of fun, and that's when I fell in love with math. It's actually really easy. Those are shortcuts. We're going to do the best we can with introducing a derivative and the derivative as a function. I know it can kind of give students a hard time, but on the other side of that, to me, section 3.3 is like the easiest. Once you get it, those are shortcuts for calculating the derivative. They go really fast and they're a lot of fun. A lot of time, again, students do typically kind of get intimidated by the intro to it, but once you get on the other side and you just kind of do the best you can with the intro, to me, the derivatives are a lot of fun. They go really quick. You'll see the question, you can pretty much just write the answer a lot of times. Okay. So we're going to start with section 3.1, introducing the derivative. In this section, we return to the problem of finding the slope of a tangent line to a curve introduced at the beginning of chapter 2. This problem is important for several reasons. We identify the slope of the tangent line with the instantaneous rate of change of a function. Okay. The slope of the tangent lines as they change along a curve are the values of a new function called the derivative. And then looking further ahead, if a curve represents the trajectory of a moving object, the tangent line at a point, let's go like this. Yeah, this is what. The tangent line at a point on the curve indicates the direction of movement. So this black line here, we have, that's going to be our function, right? So then we have the slope of the tangent line and instantaneous rate of change are negative. So over here, like if we were considering this point, remember a tangent line is a line that crosses a graph at one point in this fashion. It doesn't cross it hard like this. If it crossed it this way, we did not consider this a tangent line. But a tangent line is going to intersect a curve like this, where it gradually grazes the curve, right? So this red line is our tangent line. Notice that the slope of this line is negative. So the slope of the tangent line and instantaneous rate of change, these are negative in this context. Approximately right here, if we had a tangent line, that slope would be approximately 0. It kind of flattens out. The slope over here of the tangent line is positive. And then in a future discussion, when we consider the slope of the tangent line, that's gonna give the direction of motion. So this one is heading in this direction. At this moment in time, the object was heading in this direction. At this moment in time, object is heading in this direction. Say we have a moving object as the blue line. All right. Okay. Hopefully that was okay. So in section 2.1. we use a limit definition. We use a limit to define the instantaneous velocity of an object that moves along a line. Recall that if s of t is the position of an object based on time, then the average velocity of the object over time is going to be given by this. So the average velocity over time is going to be the position. Basically, it's like y2 minus y1 over x2 minus x1, right? So it's like the average. It's like the rate of change or slope from college algebra. Then it says the instantaneous. So again, this was the average velocity, but then the instantaneous velocity when t is equal to a. So this is as a gets closer and closer. Or let me see. This first one was as t got closer and closer to a, and then this is when t is equal to a, right? So the instantaneous velocity is going to be the limit as t approaches a of essentially the same function. We also learned that these quantities have important geometric interpretations. The average velocity of the slope is the secant line through the point a s of a and t s of t on the graph of s, and the instantaneous velocity is the slope of the tangent line through the point a comma s of a. All right. So a secant line is going to be a line that intersects a curve more than once. A tangent line is going to be a line that intersects a curve at a point in this fashion where it grazes like that. All right. So the average velocity is the same as the slope of the secant line, y2 minus y1 over x2 minus x1. Instantaneous velocity is going to be the slope of the tangent line, and basically that's going to be the limit as t approaches a. So as our t gets closer and closer to a, the slope of the tangent line is going to be described by this limit as t approaches a of y2 minus y1 over x2 minus x1. Okay, so we have this example. Let's give this a go. Let's see. Let me start with my paper. That looks good. That's what I want. So in this example, we have instantaneous velocity and tangent lines. A rock is launched vertically upward from the ground with an initial speed of 96 feet per second. The position of the rock in feet above ground after t seconds is given by this function. So this is our position function. Consider the point 1, 80, where 1 is what, after seconds? So at 1 second, we should be at 80 feet on this curve. Find the instantaneous velocity of the rock 1 second after launch, and find the slope of the tangent line to the graph of s at p. And then find an equation of the tangent line at part A. Find the instantaneous velocity. So we just said that the instantaneous velocity should be the limit as t approaches a. Let me see. We just said. Okay, let's do this first. Let's do the limit as t approaches. In this case, our a is 1. Let me think about it. Give me the point this on the curve. Is this the limit as h goes to 0? I'm gonna glance at it just to make sure I'm thinking about it right. That's what I was doing. That's fine. That's fine. Okay. Okay, I see. Okay. So yeah, let's go ahead. Let's go ahead and go with it. So for example 1. So we're gonna say example 1a. So the instantaneous velocity. So that means we're talking about the limit as t approaches. In this case, actually, I want to thin up that line a bit. One more. Let's go here. So we're going to say the limit as t approaches. Our a in this case is going to be 1. Let me see. It's going to be s of t minus s of 1 over t minus 1. All right, so we just need to evaluate this limit. Okay, so then this is going to be the limit as t approaches 1 of, now what is s of t? Here it is. S of t is negative 16t squared plus 96t minus s of 1 is going to be negative 16 times 1 squared plus 96 times 1, okay, divided by t minus 1. Let's just keep going and see where this goes. Oh, we need some space. Add a page. There should be a quick button somewhere where you can quickly add a page without having to open up that menu. Anyway, let's see. Let's do our simplification. So this is going to be, and I'm going to continue. This is fine here. This is going to be the limit as t approaches 1 of, let's see, nothing happens with that negative 16t squared for now. 96t stays as is. So let's handle this parentheses. 1 squared is 1. So that's basically negative 16 plus 96. That's what, 80? Divided by t minus 1, okay? Can we factor this? Now we do have a GCF. It looks like we could factor out, let's see, is there a 550 plus? Yeah, we can factor out, I think it's 16 from all of these. Let's factor out a negative 16 and see what happens. So this is the limit as t approaches 1. It looks like we can factor out a negative 16 from everything. We're going to be left with, if this is true, this is going to be t squared. If that's 5, I think that's a 6, right? Plus 6t. Nope, nope, nope. So it's going to be minus 6t plus 5. I think this is right? 60 plus 36 is 96. 50 plus 30 is 80, okay? Divided by t minus 1, okay? So going forward. So it looks like we can factor. So let's go ahead and factor. We have the limit as t approaches 1 of, we got this negative 16. Negative 16. Looks like we can go something like this. T. This plus here means our signs are the same. This tells us that the larger number is negative. So if they're the same, that means they're both going to be negative. Two numbers that multiply to give us 5 and add to give us 6 are 5 and 1. I think we are just about golden. T minus 1. What do you notice? Boom, just like that, right? So we keep going. We get the limit as t approaches 1. We have this negative 16 times t minus 5 over, oh, that's it, right? Because everything else is gone. So now we can use those rules that we had before, and we can actually just plug in the 1, because we couldn't plug in 1 before because we would get a 0 over 0, and then, so that means we have to manipulate it until we can plug it in. So then here we have what? Negative 16 times 1 minus 5. That's what, a negative 4. So let me see. 40 plus 24 is 64. Let's see. What are the units there? So it should be feet per second. Yeah, feet per second. Okay. That's what I got when I did that one. Let me go ahead and move into B, and then we'll go back and compare. Find an equation of a tangent line from part A. So just want to think about the units. I think I'm going to leave it as A. As T approaches A. And think about it. From part 1. I'm going to glance at the answer. Oh, okay. So if that's the slope, right? That's our M? Yes. Okay. Duh. Okay. So in part B, we're asked to find the equation of the tangent line. Notice the key word there is line, right? It's a straight line. So this 64 is the slope of the tangent line. This is the slope of the tangent line. So then in part B, I was totally about to go somewhere else. So in part B, if we want the equation of the tangent line, our slope, what is this, instantaneous, right? Let me try to keep my, yeah, that should be the slope of the tangent. So this is the slope of the tangent line, which is going to be 64. We also have the ordered pair. What do we say? 1, 80? Did we even use that 80? We did. Oh, I sat up there and calculated that. Anyway, didn't have to calculate that, but that's okay. So we have the ordered pair 1, 80, right? After 1 second, the position was 80 feet, off the ground? Okay. So, from college algebra, I'm just going to use, I'm a fan of, well, I guess, there's a couple, I'm just picking it. I'm going to do this one first. I'm actually going to start here, y equals mx plus b, just to be different from the text, all right? So I think we have our slope. We have that the slope is what, 64. When x is 1, y should be 80. Only thing we don't know is the y-intercept, all right? So let's go ahead and solve for the y-intercept. So then B is going to be basically 80 minus 64. What is that? 16? So then it's going to be y equals 64x plus 16. This should be the equation of the tangent line. Okay. Let's see, how do we do? So for part A, we got our 64. And then for part B, y equals 64t plus 16, 64t. Oh, t. Okay. So yeah, I forgot the units. Let's do t. Okay. So we got those. Let's move forward. I am doing my best to honor the time. I do have a class that starts in about an hour. I would like to finish these in an hour. I might go over just by a little bit. So that way we can kind of go at a leisure pace, making our way through these sections. Okay. And let's just get rid of this for right now. Okay, I'm going to let that be. Let's move on to this one. So consider this curve, f of x, and a secant line intersecting the curve at the points a f of a and x f of x. All right. So again, secant line, it intersects a curve at more than one point. The difference between f of x and f of a is the change in the value of f as a changes over the interval from a to x, while x minus a is the change in x. As discussed in chapters 1 and 2, the slope of the secant line between these 2 points is going to be given by this. The slope of the secant, basically y2 minus y1 over x2 minus x1. And it gives the average rate of change in f on the interval from a to x. Okay. Figure 3.5 also shows what happens as the variable point x approaches the fixed point a. If the curve is smooth, it has no kinks or corners, the secant line approaches a unique line that intersects the curve at P. This line is called the tangent line, right here, 3.5 over to the left, right? So we have this curve, right? And we're considering the secant line. So the line that crosses it. All of these green lines are secant lines. So as this second point Q gets closer and closer to this point P, again, as X gets closer and closer to the fixed point A, we have, where is it? The slope of the secant is, notice this green line gets closer and closer to the slope of the tangent line, which is our red line, right? Okay, so we have the slope of the tangent line is going to be limit as x approaches the fixed point A, basically y2 minus y1 over x2 minus x1. Because the slope of the line at P is also called the instantaneous rate of change in f at the point A, because it measures how quickly f changes at A. The tangent line has another geometric interpretation as discussed in section 2.1. If a curve is smooth at a point, then the curve looks more like a line as we zoom in on P. The line that is approached as we zoom in on P is the tangent line in figure 3.6. A smooth curve has the property of local linearity, which means that if we look at a point on the curve locally by zooming in, then the curve appears as a line. Okay. So let's glance at 6.3.6 real quick. So if we were to zoom, so we have a curve, but if we zoom in, it's going to kind of behave like a line. That is what we mean by the tangent line. All right. Let's kind of look at this part here. Okay. Oof. So let's talk about the rate of change and the slope of a tangent line. So the average rate of change in f on the interval from a to x is going to be slope of the corresponding secant line, right? y2 minus y1, x2 minus x1. The instantaneous rate of change in f at a point A is going to be the slope of the tangent line, which is going to be the limit as x approaches a of that same y2 minus y1 over x2 minus x1, which is also the slope of the tangent line. So the instantaneous rate of change is going to be the slope of the tangent line at a fixed point A, f of a, provided this limit exists. The tangent line is a unique line through this point with the slope of the tangent. Its equation is going to be given by y, basically this is the point slope formula from college algebra, right? We got the slope of the tangent, and then we have the a and our f of a. Okay, let's can we get working an example? Here we go. So we have this example. Let's go like this for right now. Let's see, find an equation of a line of the tangent line to this graph. So basically, first we need to find the slope, find the tangent, find the slope of the tangent, and then use that slope to find. So essentially the same thing, right? So find the slope of the tangent line when a is 2, and then use that slope to find the equation of the tangent line when a is 2. Okay? So first let's find the slope. We're essentially just redoing what we just did. At least that's what I'm going to do. I'm going to do that first and see how that works for me. So if we want the slope of the tangent line and not the slope of the secant, so let's say the slope of the tangent line is going to be given by the limit as x approaches a of f of x minus f of a over x minus a, all right? So we're using like the limit as x approaches a between the 2 points. Now our f of x in this case is going to be 3 over x, and we want to consider the point 2 comma 3 by 2, all right? Okay. So then this is just going to give us the slope of the tangent line. Again, that's going to be the limit. In this case, it's going to be the limit as x approaches 2 of, let's see, we're going to have f of x minus f of 2 over x minus 2. Now notice we can't just plug in 2 because we're going to get 0 over 0. So then, let's see, let's continue. I guess we'll continue here. This is going to be the limit as x approaches 2. F of x is going to be 3 over x minus, now f of 2, I think I forgot well, it's not nothing fancy going on here, over this over x minus 2. Okay, let's go ahead and do some algebra real quick and simplify this. This is going to be equal to the limit as x approaches 2. Now we can get a common denominator of what? 2x. Okay, so we're going to multiply the top and the bottom by the LCD of our fractions. We're going to multiply the top and the bottom we're going to multiply by 1 in the form of 2x over 2x, okay? Keep in mind, we're going to distribute, and let's do the same thing down here. We're going to distribute, all right? So I multiply by 1 in order to clear out our fractions, okay? So then on the top, the x's cancel, and we're left with 6. The 2's cancel, and we're left with minus 3x. On bottom, hopefully this isn't making it worse. We get a 2x squared minus 4x. Let's just see where it goes. Okay. I think actually on bottom, I'm going to leave that as expanded. So I'm going to leave it as x minus 2 times 2x. I'm going to just leave it like that. Okay. Let's see. We can factor out what, a 3 from both terms on top? Hopefully this will work for us. So this is going to be the limit as x approaches 2. If we factor out a 3, we're left with 2 minus x. So instead, see how we have 2 minus x and x minus 2? When that happens, instead of factoring out a 3, I'm going to factor out negative 3. If we factor out negative 3, then we'll get our desired x minus 2. And we always check by multiplying back. Okay. So if we, real quick as a quick check, notice that negative 3 times x is a negative 3x. Negative 3 times negative 2 is positive 6. So we're in the clear. Now we're getting our desired effect of this canceling this, all right? And I think now we're ready to apply those limit definitions that we talked about last time. So this is going to be the limit as x approaches 2. On bottom, we're going to have 2x. On top, we're going to have negative 3. So then now we're ready to just plug in. We get negative 3 over 2 times 2, which is negative 3 by 4. Let's see. So this is just the slope, right? But we want the equation of the line. So now we want to use that point 2 comma negative 3. I'm just going to do it the same way I did it. Okay, I can do the other one. So the other one was y. Let me see, what was it? Because I keep wanting to do it in. Okay, yeah. Y minus f of a. I'm gonna rewrite it the way we did it in college algebra. So y minus y1 equals m times x minus x1, right? Where our slope, in this case, our slope is the negative 3 by 4. And we're going through the point 2 comma 3 halves. This is going to be our x1. This is going to be our y1. Okay? So then we're going to have y minus the 3 halves equals the negative 3 by 4 x minus 2. Boom, just like that. Ooh, good job. Ooh, this is fun. I don't know about you all. I hope you all are having fun. I know that you're probably not. But I just encourage you to do your best. You know, you have to actively go and get it. Like, just ask me questions. Email me, contact me, 10 office hours, all that jazz. Just reach out. Do your best. Okay? All right, so let's go ahead and simplify this. So then we get y equals, we get this a negative 3 by 4x. What is it, 6 by 4? Or let's do plus 3 by 2 plus another 3 by 2. Ultimately, we get y equals a negative 3 by 4x, 6 by 2, which is 3, plus 3. We get this equation. Let me see. What was our original? So in our graphing calculator, let me see. Find an equation of a tangent line to the graph when x at 2. Okay. I want to show you something really quickly. Hopefully, it doesn't take too terribly long. So say we wanted to like verify something like this in our graphing calculator. Yeah, there it was. Oh, that's okay. So I'm just going to show you what this looks like. So we found the equation of a tangent line at that point. So what we're going to do is type in the original function. It's 3 divided by x. So we have this 3 over x, right? And then we also found the equation of the tangent line should be this negative 3 by 4 x plus 3, all right? So if we look at the graph, we should have a curve with a tangent line at 2 comma 3 halves. So there's our curve. And then when x is 2, the tangent line, you see how it just gently grazes our graph? So the second line that you saw drawn was the tangent line that we found. Okay. So yeah, that's pretty good. You can also use GeoGebra for stuff like this as well. And it's a lot of different tools that are out there. So the negative 3 by 4, we got that. And then for part B, you see it here. Y equals a negative 3 by 4 x plus 3. We can also say that the instantaneous rate of change of f at x equals 2 is a negative 3 by 4. Okay, so that's one form of the instantaneous rate of change at a point. There's another one. That's another form for an equation for the instantaneous rate of change at a point. So an alternative formula for the slope of the tangent line is helpful for future work. Consider again a curve and a secant line. So we have this secant line, right? As this point Q gets closer and closer to this point P, we have our fixed point A, and then we're going to have A plus some change. So as this change H goes to 0, this second point gets closer to the first point. So we're going to, an alternate way of doing the slope of the tangent line at a point is going to be the limit as H tends to 0. Again, H is our change in X. So as that change goes to 0, then this is going to become our slope of our tangent line. So this is an alternate way that we talk about derivative. The slope of the secant line, PQ, using a new notation, f of a plus h, where h is just going to be a change in x minus f of a over, again, that change in x. As that change goes to 0, the variable q gets closer and closer to p. So then the slope of the secant line approaches the slope of the tangent line. So therefore, the slope of the tangent line at a comma f of a is going to be the limit as h goes to 0, basically y2 minus y1, and this is the change in x, which is x2 minus x1. Okay. So let's look at this one. So the average rate of change on the interval a and a plus some change is going to be f of a minus f of a plus h minus f of a over h. This is called difference quotient. We mentioned this in college algebra, right? We actually worked a few examples that were like this in college algebra. And then the instantaneous rate of change of f at a is going to be the limit as that change goes to 0 of that same function, okay? So we're asked to find the equation of a line, but in this case, we're gonna do the difference quotient. Let me think about it. Oh, so yeah, we're gonna use this this term here, this function. Okay, let's give this one a go. I think I'm ready for this one. This one feels good. Go like this. So find the equation of the tangent line to the graph. Now our f of x is x cubed plus 4x at the point 1 comma 5. If we're going to use the difference quotient definition, the slope of the tangent line is going to be given by the limit as h tends to 0 of f of x plus h minus f of x all over h, right? Now notice we can't just plug in 0 because then we're going to be dividing by 0. It's going to be undefined and we can't simplify it. So let's find our f of x plus h. Let's just do that by itself off to the side. I'm going to use like this color. So if we focus on f of x plus h, okay, so then we're going to have x plus h cubed x plus h cubed, let me see, plus 4 times x plus h. So it looks like we need to expand that out. So this is going to be x plus h times x plus h times x plus h plus 4x plus 4h, okay? This is going to be, I usually like to do this one in the following way. If I expand the last two with a FOIL, we're going to get x squared plus 2xh plus h squared, okay? 4x, 4h. And then we're going to distribute. So x times all of these and h times all of these, okay? So then we'll get x cubed plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed plus 4x plus 4h, okay? Let's combine like terms. X cubed is alone. We got an x squared h here, and we got an x squared h here, which becomes 3x squared h. We have a xh squared and another xh squared, and those become 3xh squared. I think the h cubed is alone, and then the 4x and the 4h. Okay, I think that's as far as we can take those. So now we're going to take this and put it back into our difference quotient, all right? So then, and let's add a page. So then, the slope of the tangent line is going to be given by the limit as h tends to 0 of, now let's see, we're going to have, I'm just going to copy and paste all this. I think that'll be easiest with this technology that I have. Let's copy, paste. Okay. So that's f of x plus h. Then we're going to say minus, oh, I'm totally running out of space. Minus f of x. So we want to say it's going to be minus x cubed minus 4x. That's what we need to introduce. Let's just cut that. Need to paste. It needs to go right there. Just had enough space. Okay. So that was the part that we needed to add. We're going to say all divided by h. Now when we add that part that we added, the following happens. We got this negative x cubed and x cubed. We got negative 4x and 4x. They cancel. The whole point is, if we do this properly, we should be left with something where everything has an h, as h tends to 0, right? And let's kind of line this up a little bit better. Kind of like that, okay? So now what we're left with, this is going to be equal to, this is going to be equal to the limit as h tends to 0. We have, now we can factor out an h from everything. We're going to be left with 3x squared, that h is gone, plus 3xh plus h squared plus 4. Notice that everything that was left had an h, so I went on and factored it out. And we're going to say divided by h. See, the whole point is that we wanted this effect to happen. So now we can do this. And now we should be golden at this point. Stay golden, point of away. Anyway, so now we have the limit as h goes to 0. We got this 3x squared plus 3xh plus h squared plus 4. That's going to be equal to 3x squared. So basically our h's become 0. So essentially, this is going to go to 0. This is going to go to 0. So we're going to be left with 3x squared plus 4. And let's see what the question asks us to do. Find the equation of the tangent line, and I think we're done. We let a equal 1 in definition 2, and first find 1 plus h after expanding. Now they did theirs different. I'm going to go with this. Let me look at the original. 3x squared plus 4. 3x squared plus 4. Yeah, we're good. I'm going to go with this one. Oh. This would be 9. Okay. So let's see how did the book do it. So now they let a be 1 in definition 2, and they first found f of 1 plus h, and they have something like that, right? Substituting that in, yeah, they did theirs different. That's interesting. We did ours different ways, and we were able to, oh, so that was just a slope. I guess I skipped ahead. The tangent line has a slope of 7 and passes through the point. Its equation is this. Maybe I'm wrong. Let me look at it. Let me look at what did I get again. That's the, what did the question ask? Find an equation of a line. Am I looking at the right thing? Find an equation of a line to this. Maybe I'm not looking at the right thing. Let me see. Okay, that's fine. So they found the slope first. So the tangent if the tangent line has a slope of 7, I found the derivative. Daggone it. I found the, okay, so what I found was the derivative. Equation of the tangent line. Okay. Let me think about what I'm doing wrong here. So what this is, okay, so this is going to be the derivative. So then we need to let x be, so when x is 1, right? Okay, so yeah, I am kind of jumping ahead. Let me get rid of this. I'm going to keep this. I'll highlight it like this. So now, if we let, so I'm going to say just let x be 1, right? If x is 1, the following is going to happen. So we're going to have 3 times 1 squared plus 4. And that's going to give us our 7. So this is going to be the slope of the tangent line. Okay, when x is 1. So then I'm a fan of the y equals mx plus b. Okay. So then the slope is, let's see, this is when x is 1. So if our slope is 7 and the ordered pair, we had 1, 5. So this was 1, this was 5, this was b. So then b is going to be -2. So then y is going to be 7x minus 2. This is the slope of the tangent line. What I found was a derivative, which is telling us the slope across the function. So given any x, that will give us a slope. So that's how it's like. So this thing that I found here, this tells us the slope given any x from the. This tells us the slope of the tangent line given any x for this function, right? So this is the slope of the tangent line given any x. So then I was like, okay, well, that's why I went back and said, okay, well, let x be 1. So then that means the slope at the instantaneous rate of change at that point is going to be 7. So then I had my slope. Then I used that slope to find the equation of the line. 7x minus 2. And you see it right here, 7x minus 2. Okay, so mine was a little bit roundabout, but that's where we're heading, and it's actually going to be much easier than that. Okay, that's just like, so, you know, do the best you can with that concept, but don't be intimidated by it. Once we get to section 3.3, in my opinion, it gets much easier, at least at that point. Okay, I got about 40 minutes remaining. Okay, so let's kind of look at this. So the derivative of f, denoted by f prime of a, is given by either of the two following limits, provided the limits exist and a is in the domain of f. We can either say that f prime is going to be the limit as x approaches a of basically y2 minus y1 over x2 minus x1, or we can say it's the limit as h tends to 0. This is what I just did. F of a plus h minus f of a over h, right? So I use this one, but you can use either one. If f prime of a exists, we say that f is differentiable at a. The limit definition, the limits that define the derivative of a function at a point are exactly the same limits used to compute the slope of a tangent line and instantaneous rate of change of a function at a point. When we compute a derivative, remember that we are also finding a rate of change and the slope of the tangent line. So again, for me, again, the derivative is the slope of the tangent line at that point, right? So in this example, let's see. So we have this function. We're asked to compute f prime of 2, the derivative of f when x is 2, and use the result to find an equation of a tangent line to the graph at this point. Okay. So they said they're going to use definition 1. So this should be the limit as x approaches a, right? Okay, let's use this definition 1 to solve this one. So we have this function. We got the square root of 2x plus 1, and when x is 2. So if we use the limit definition, definition 1 says the limit as x approaches a, let's clean it up a little bit. The limit as x approaches a of f of x minus f of a over x minus a. Let's give this one a go. So if we apply this to ours, this is going to be the limit as x approaches what? 2? As x approaches 2 of f of x minus f of 2 over x minus 2. Okay, let's kind of move forward with this idea. This is going to be, and notice we can't just plug into 2 because we're going to get 0 over 0. So we need to manipulate it. So then we're going to have the limit as x approaches 2, f of x is going to be square root of 2x plus 1 minus, now f of 2 should be 3, right? Square root of 4 is 2. Yeah, it's going to be a 3 over x minus 2. Okay, let's see. Can we rationalize or use the conjugate? I'm thinking conjugate here, right? So we have the limit as x approaches 2. We have the square root of 2x. 1 minus 3 is going to be negative 2 divided by x minus 2. So let's multiply the top and the bottom by the conjugate and see what happens. So the conjugate in this case is going to be square root of 2x plus 2. Square root of 2x plus 2. All right, let's just do this and see what happens. So I'm going to leave the bottom in expanded form, but the top I'm going to expand it out. is going to be the limit as x approaches 2. So that the first term is just going to be 2x outer. So we're going to have plus 2 root 2x, and then we're going to have minus 2 root 2x. And then the last is going to be minus 4. Notice this cancels this. I'm going to leave this expanded, root 2x plus 2. Okay. So then the limit as x approaches 2. Now on top, the radical is gone. We have 2x minus 4. Oh, okay, yeah, we're almost there. X minus 2, root 2x plus 2. Okay. My eyes are burning. Okay, so now on top, we can factor out a 2. We're going to have the limit as x approaches 2, 2 times x minus 2, and now we should be there. X minus 2, square root of 2x plus 2. And we should notice this. This finally cancels that. So then the limit as x approaches 2. Now we can just essentially just plug in. We got the square root of 2x plus 2 under 2. And this is going to be basically the square root of 4 plus 2 under 2. That's going to be a half. So this is going to be the slope of the secant line, right? Or this is going to be the slope of the tangent line. Okay, so the slope is there. So what are we finding? Compute f prime of 2. So that should be 1/2. We got a half. Oh, come on, delete. Okay. And use the result to find an equation of the tangent line. So that's the slope. So then when we want the equation of the tangent line, we're going to use y equals mx plus b. Okay, in this case, our m is a half. And we want to go through the ordered pair 2, 3. Okay. So that means we're going to have 3 equals 1/2 times 2 plus b. That's a 1. So then b equals 2. Okay. So then we're going to have y equals 1/2 x plus 2. Now you can graph this like I did the other one just to make sure that it looks proper. This line should graze our curve. Okay. I just want to kind of glance at the answer because I am kind of short on time. So we got the half, and we got 1/2 x plus 2. Okay. So if we were in each other's presence, this will be the time. I might just limit this one to maybe just to section 3.1 for today, because I am a little short on time, and we have been going. Do I have my time here? Can I rewind? 30. Yeah, we've been going for about an hour, and the class is only an hour and 25 minutes. So. Okay. So I think what I'll do for today, I'll just limit it to section 3.1 for today, and we'll pick up. We're not just done, but I'm just noticing the time and the rhythm of all of these. Ugh. Okay. Let me see. How many more for this section? That was what, 5? Is it out of order? Oh no, it's just the same page. 5, 6. I think 6 is the last one. Yeah. Let's go ahead and talk about 5. So interpreting the derivative. The derivative of a function at a point A measures the instantaneous rate of change in f at A. When the variable associated with the function represents a physical quantity, the derivative takes on a special meaning. For instance, suppose T describes the water temperature at a depth D. Then G prime measures the instantaneous rate of change of the water temperature at depth D. The following examples illustrate this idea. Instantaneous rate of change. Sound intensity I measured in watts per square meter at a point X measured meters at a point X meters from a sound source with an acoustic power P is given by this. A typical sound system at a rock concert produces an acoustic power of about P equals 3 watts. Compute I prime of 3 and interpret the results. So that's going to give us the instantaneous rate of change when X is 3, okay? I think for the sake of time, I think I might just kind of, let me see. I think I'm actually going to do this one. So basically it's saying compute I prime of 3. We do have 2 points. Okay, I'm just going to use the one that we just used. Let me see which one are they using. I get that. Yeah. Okay. Oof. All right. So we're going to use the definition where we say we're going to use the limit as x approaches a of f of x minus f of a over x minus a. And in this case, should be x is 3, right? Okay. Let me do it the way that they're doing it as well. I forgot. I do kind of do mine a little bit different. So we got to say, oh, they're using the h definition. Okay. We're going to say a plus h. So let's use that one instead. So we're going to use we're going to say the limit as h tends to 0 of f of a plus h minus f of, should be f of a all over h, right? Okay, so in our example, this is going to be the limit as h tends to 0 of, our a in this case is 3, so we're going to say f of 3 plus h minus f of 3 over h, okay? So then f of 3 plus h, so I'm going to look at that as a constant, right? We're going to say 3 over 4 pi. Now we got 3 plus h. We're going to say 3 plus h squared minus 3 over 4 pi times 3 squared. Okay, I'm going to go with this. Let me see. Now we could factor it out from both, and I probably will, and hopefully, and this is going to be, it's going to be the limit as h tends to 0 of that over h, okay? Let me factor out the 3 over 4 pi from both terms. Let me add a page. Where am I working? Here? No. Yeah, this one, right? Where is it? Oh, there it is. Let's add a page. Okay, so then this is going to be the limit as h tends to 0. We're going to factor out that 3 over 4 pi. So we're going to have 3 over 4 pi. What's left, we're going to have this 3 plus h. And this thing needs to be here. Okay. think this is okay. All over h, okay. Am I doing this right? Okay, let's go ahead. Oh, my eyes are burning. Let's go ahead and expand that binomial. I'm trying to think. Okay, actually, what I'm going to do, I'm going to multiply by 1. First thing I want to do, I'm going to, since I'm dividing by a fraction, I'm going to use keep change flip, because there's a couple of routes we can do, but I'm going to do keep change flip. I'm going to rewrite it in the following way. Limit as h tends to 0. We're going to have 3 over 4 pi h, all right? And then times, let's see. We're going to have this 3 plus h squared under this minus 1 over 9, okay? Let's just go ahead and combine, add fractions. So let's get a common denominator. It's going to be 9 times that. I'm going to leave it expanded. It's going to be the limit as h tends to 0. We still have this 3 over 4 pi h. Common denominator here is going to be 9 times 3 plus h squared. So that means the one on the left, we multiply the top and bottom by 9, so that becomes a 27, minus that top and bottom by 3 plus h squared. So we're trying to get to a point where we can factor out. Let me expand the top. I think that'll get it going. Let me expand the top and see what happens. So the limit as h tends to 0, 3 over 4 pi h. Now that's going to be 27 minus, that's going to be a 9, 6h plus 6h plus h squared over, I'm still going to leave this as this, 3 plus h squared. Limit, hopefully we can, I think we can get there. I'm going to keep going. Limit as h goes to 0, 3 over 4 pi h. Now we're going to have 27 minus 9. Let me just go ahead and calculate that. That would be 17, so 18, right? And that's going to be 18 minus 6h minus h squared over 9 times 3 plus h squared. I keep moving that for some reason. My eyes are burning right there. Let's I'm trying to think. Let's go ahead and factor out a -1 and see can we factor. So this is going to be the limit as h tends to 0. We got this -3 over 4 pi h. We're going to have h squared plus 6h minus 18. 3 plus h squared. Okay. Now let's try to factor that top, right? Can we factor it into something of this form? We're going to have h and h. One's going to be plus, one's going to be minus. Two numbers that multiply to give us 18 and add to give us 6 is it 6 and 3? 9 and 2? Nope. Are these numbers proper? 1, 2, 3. Let me make sure I got my numbers right here. Oof. Stop. Oh, I see that 9 can go. But that's not the thing that is getting in my way. Subtract 2 more is 18 minus 6h minus that. If we factor out a negative, h squared plus that minus that, 6 and 3. You sure this is 6h? 6. 3 plus h. I feel like we made a mistake somewhere because it's not able to factor. We're missing something somewhere. I'm going to glance at the answer for the sake of time. Well, we did that one. Let's see, there's that. They factored out that like we did. 6 plus h. 6 plus h. I feel like I made a mistake. 3 plus h squared, right? That's going to be a 9. Did I? Oh, maybe that's where I messed up. 27. Let me back up. Okay, I factored that out. Let's see. 9, okay. I move that over there, that's fine. This times that, so top and bottom by 9 there. 9 times 3 is 27. 3 plus h squared. Okay. They had 6. I'm not seeing something. If you expand that, 9h 3 times h times 2 is this. Okay. 18, I think that's fine. I don't know if I should put that 3 back. H squared plus 6h minus 18. And I don't think I can factor this. 9 and 2 is a 7. If that was a 7, we would be there. Let me look at theirs. Right here. 3 plus h. Let's see. So 1 over 3 plus h squared. We did this. We did that. 9 minus 3 plus h squared. Do we have that? 9. Why is our 3 still there? Oh, okay. Whew, I found a mistake. I was like, yeah, we definitely had an extra term in there. I found it. I didn't factor properly. That's what happens though. Like you just have to work it and keep trying. I found the mistake. Okay, so what I'm gonna do, I'm gonna scrap all of this. Ugh. I didn't factor properly. I missed a 3. I'm gonna delete this and start back. So this guy right here. So when I factored out that 3 over 4 pi, this should have been a 1. I'm going to mark that in red so it stands out. That should have been a 1. And that's now let's go back and fix it. Okay, I think we might be okay now. Okay, so now this is going to be the limit as h tends to 0. So top and bottom by 9. So basically it's going to be 9 minus 3 plus h squared. I think we're much better now. And then we're going to have 9 times 3 plus h squared, okay? And over here we have the 3 over 4 pi, and like that. So, and again, I don't mind leaving stuff like that in presentations because that's what happens when you're doing this stuff. It happens, you have to like pause, like, wait a minute, this isn't adding up. Let me go back and check my work. And you just have to keep coming back until you can find where you made the mistake. And so that's just what happens. Let's kind of keep going. Okay. So now if we expand this, now we're going to have the limit as h goes to 0. We got this 3 over 4 pi. Let's see. 9 minus, that's going to be 9, 6h. So minus 6h minus h squared over 9 times 3 plus h squared. Okay. So now these guys are gone. We can honestly factor out a negative h, and I'm still missing an h. So there's really, let's say divided by h like that, and now I'm just going to put my h there. So now we can factor out the negative h. We're going to have the limit as h tends to 0. We're going to have 3 over 4 pi h. We're going to factor out a negative h from those two. Negative h on top. We're going to be left with 6 plus, I think we're okay. Yeah, 6 plus h divided by 9 times 3 plus h squared. Okay, I think we're okay. The whole point when you're doing this limit as h goes to 0, you want to get to a point where you have an h on top that's going to cancel the h on the bottom. Once that happens, then that means you're on the right track. All right, that's what you're kind of looking for. Okay, I'm going to do some other cancellations. We got this 3 is going to turn this 9 into a 3. I can't see anything else immediate, so let me just try to be neat. So this is going to be the limit as h tends to 0. On top, we're going to have this negative times 6 plus h divided by, we have 4 pi times 3 plus h squared. Now we're ready to say the limit as h. Now if we say we pass the limit as h goes to 0, so then this is going to go to 0, this is going to go to 0. I think we're okay now. This is going to be negative 6 over 3 squared is 9 times 4, 36 pi, which becomes negative 1 over 6 pi. Let me see. This is what I got when I did it. So I found that mistake. I was like, I knew I was missing something. Okay. I just want to kind of glance at theirs. We got a negative. Now let's see. What is that? That's going to be the slope. It says compute I prime of 3 and interpret the results. So that's the rate of change. Instantaneous rate of change. Yeah, let's just look at the thing here. So, oh, that's 4. This one, they get negative 1 over 18 pi. Am I missing some other terms? 18 pi. There's a 3 missing somewhere. There's a 9 times 4 is 36. We're missing, oh, that 3. Nope, that one got canceled. Oh, there it is. I see the 3 that I'm missing. I'm missing, let me put this in red. This 3 right here. And that 3, I'm going to say it's going to be here. And let me just kind of fix the answer. Man, I'm just chock full of mistakes in this last little bit. Delete. So that's going to turn this into, so let's see, let's do it like this. The 3 is going to turn the 6 into a 2. And that's what, 18? This is going to turn this into an 18. So we're going to be left with negative 1 over 18 pi. Okay. So that one, I just needed to be more meticulous, kind of slow down, and delete. There we go. Needed to be more meticulous, slow down, and kind of take my time. The units there are, okay, I think I'm out of time as well. These are watts per meter squared. Yeah, I'm just gonna kind of let that be. I think I'm gonna just leave this one as an exercise just because I'm out of time. Okay, example 6. I think because I wasted so much time on that mistake that I made, but I'm glad that I found it, so that that's just how it happens sometimes. You just kind of have to do the best you can. Okay, a lot of that was algebra. The concepts remain pretty consistent throughout the lecture for the day. It's just definitely made the mistake. I'm gonna actually stop here, and we'll just have to know that next time we have to pick up with section 3.2, the derivative as a function. Okay. So on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Okay. So again, as a reminder, on Moodle, we have a participation and honesty quiz that we need to take. Also, we're going to be on the lookout for another quiz later this week. And hopefully, just be sure to get your assignments submitted on Pearson. Before the due date, you can get whatever score you want. You get unlimited attempts at all the assignments, and you can take it as many times as you want until you get whatever score you want. After the due date, the highest that we can score on any assignment is an 80, which is a low B, and the highest we can score on any exam is a 79, which is a high C. Okay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day.